What happened, Swan?
Man, I missed the bus. The next bus is gonna come in 40 minutes, and I need to get to my meeting in 20 minutes.
You know what? There's this thing called a magnet train. It runs on superconductors, and you'll never be late ever in your life.
What? Superconductors? What are those? A superconductive compound is able to conduct electricity without resistances once it's below a certain temperature. Resistance is undesirable because it produces losses in the energy flowing through the metal.
If superconductivity is achieved in a compound, then the electrical current will flow forever in a closed loop, making it the closest thing to perpetual motion in nature.
Not all materials show superconductivity. Along with mercury, the original superconductor, you can find the superconductivity effect in 25 other elements. It has also been discovered in thousands of compounds and alloys.
Each different material becomes a superconductor at a slightly different temperature, which is known as its critical temperature. The trouble with most of these materials is that they superconduct only within a few degrees of absolute zero. This means whatever benefit you gain from their lack of resistance, you probably lose from having to cool them down in the first place.
The Meissner effect is when a material transitions from a normal state to a superconductive state. That is where the material reaches zero electric resistance.
The Meissner effect in superconductors acts to exclude the magnetic field from the material. The currents which cancel the external field produce magnetic poles which mirror the poles of the permanent magnet, repelling them to provide the lift to levitate the magnet. These create a magnetic field similar to that of an electromagnet.
These currents adjust exactly to compensate for magnetic field applied inside a superconductor. The total magnetic field here hence becomes equal to zero.
As the levitation meets no resistance, the suspended magnets can be moved in many different ways and speeds, as the levitation currents can adjust to maintain suspension.
Before Josephson observed this phenomenon, it was known that only normal electrons can cross between non-conductive substances from one conductive material to another. This is achieved through quantum tunneling. If enough voltage is provided to a non-superconductive electron, it will cross the gap. When a superconducting material is cooled to its critical temperature, electrons pair off into Cooper pairs, which is any movement of one electron is matched with equal and opposite movement of another. This means the flow of a Cooper pair is a supercurrent, which is a current that flows indefinitely without the addition of extra voltage. Josephson was the first to predict if two superconducting metals were separated by a thin insulating layer. Then quantum tunneling can occur for the Cooper pair without separating the pair. This effect can be visualized if you imagine an electron as a blindfolded person trying to move through a room with multiple barriers at various locations. As the electron tries to move through the room, it encounters resistance from the objects. When a superconducting material is cooled enough, it forms a Cooper pair. Imagine a Cooper pair has two electrons who are able to communicate. This allows the electrons to flow through the metal without any resistance. Thank God that's over.
Yeah, wait, hold on. We have to see that picture.
In 1911, superconductivity was first observed by Dutch physicist Huyck Owens. He cooled mercury metal to the temperature of liquid helium, which is approximately negative 269 degrees Celsius, and its resistance dropped.
In 1933, German researchers Meissner and Ochsenfeld discovered that a superconducting material will repel a magnetic field. This in turn causes the levitation effect. In 1986, a truly breakthrough discovery was made in the field of superconductivity. Two researchers at the IBM Research Laboratory in Switzerland created a brittle ceramic compound that superconducted at the highest temperature at the time, which was 30 Kelvin. What makes the discovery so remarkable was that the ceramics are usually insulators. They don't conduct any electricity well.
Many of you might not know this, but superconductors are also used in MRIs. MRIs use small magnets which are located in the nuclei of the human body to see what's around them. The patient is put in a magnetic field, so the magnets in the nuclei, which are called spins, must be lined up. To make the fields, an electric current must flow through a coil of thousands of wires. If regular metal wires were used, they would heat so much that they would melt. This is why in all MRIs, the coil is made up of superconductive wire plunged in a very cold liquid, such as helium. Since there's no electrical resistance, this means there's no heating. If you've all seen Back to the Future, you should recall this particular scene.
Hey, stop! Little girl, stop! Look, I need to borrow your hoverboard. Where is he? Here. There! He's on a hoverboard! The board! Give me board!
The MagServe uses superconductive technology that literally has you floating. This levitation device uses a liquid nitrogen-powered superconductor to propel a skateboard-sized hoverboard across the magnetized track. The metal on the bottom of the board becomes a superconductor when treated with liquid nitrogen and placed atop the magnetic field in the track. The supercooled metal repels the magnetic track, levitating it.
The fastest train in the world is located in Japan. The train doesn't even touch the tracks and use superconductors. It levitates a few inches above the track thanks to technology that uses strong magnetic fields created by superconducting coils located and cooled on board. Astonishingly, the wagons are able to go up to 500 kilometers per hour with passengers on it.
Electricity is an essential source of energy that the modern world relies on. Unfortunately, power cables can only transport a limited amount of current. If they reach their limit, they will heat and melt. A network of superconductors would do the job much more efficiently. This is due to the fact that 1,000 times more electric current can flow through them, and that smaller cables will be able to transport more current. The reason as to why this idea is for the future and not fully in fruition yet is due to its current unprofitability, as the cables have to be cooled to become superconductive.
The significance of the topic of superconductivity is that if it is usable at room temperature, it will change the transportation industry. It will allow people to travel to places faster and more efficiently while saving energy and preventing energy loss, which in turn is beneficial for the environment. If any of you are interested to learn more, you can head on over to our website at swan0498.wix.com/superconductors. Thanks for listening.